This is a terrible. It's not a good place to record in this room.
Mark, I need to give you guys a camera just to hold. We already lost one of our students, right? Taylor's out. So that means all day today, right? We can record this and it's going to be on YouTube forever, right? And then like some random student 1 year is going to hear about this. Like, who the hell's Taylor? I think you mentioned it. Internet famous, right? Tens of people will watch this. Anyway. All right, so we were kind of knocking the rust off of OChem 1 knowledge there. We were going through and discussing a little bit about alcohols, and we talked about some of the different reactions that we started to learn with alcohols. We talked a little bit about the properties and that kind of stuff with it. Right? And so what we want to do today is kind of continue on and start to learn a little bit of the new reactions that we didn't necessarily talk about all that much last semester. I don't think we mentioned any of these, to be honest. But so a couple of new things coming here, and we'll learn a little bit of a new mechanism. Although you guys already know all these mechanisms, that's pretty much the amazing thing. There's going to be like 1 or 2 mechanisms that'll be like completely different this semester, but all the other ones, I could just give you guys the question and say, figure out what happens, right? Because you guys are familiar with the steps now, right? Find the positive, find the negative, break pi bonds, make pi bonds, make sigma bonds, break sigma bonds, that kind of stuff. None of that's really going to change, right? So there's not too much different in that sense there. But anyway, what we were discussing, or where we kind of left off last time, is just talking about, or beginning to chat about the idea of an oxidation, right? How we can take an alcohol and how we can turn it into an aldehyde, right? And we said that we don't know too many reactions so far, or we didn't know too many reactions in the first semester about how to make an aldehyde directly. Right? We learned how to make an aldehyde from an alkyne under specific conditions, and we talked about the tautomerization here, right? But we didn't learn how to take an alcohol directly into an alkyne. That's not something we discussed, right? Now, could you guys take an alcohol and turn it into an alkyne? Just go ahead and lie to me. Yeah, okay, thank you. Right. Right? Is that a set of reactions that you guys should, in theory, be able to do? Of course, right? We change the alcohol into a halide or some leading group. We put in a bulky base. We make an alkene, right? And then we do a halogenation to make the vicinal dihalides, and then we do an elimination to make the alkyne, right? And so it takes quite a few steps to turn an alcohol into an alkyne, and then turn it into an aldehyde, right? It's a 4-step process. So we'll talk about a way how to do it in 1 step, right? Where we don't have to do any other significant transformations, okay? All right, so let's think here for just a second, okay? So if we are following the arrow up here, right? This is an oxidation, right? So what is an oxidation? What do you guys remember? Okay, it's a loss of electrons, right? And so the counterpoint to an oxidation would be a reduction, right? So if we pointed an arrow in the opposite direction, where you go from the aldehyde to the alcohol, that would be the reduction, okay? Okay, what's losing electrons? Right?
Carbon.
The carbon? What do you mean?
So in the oxidation, the electrons are going to go all towards the more electronegative atom, which would be the oxygen.
There's already an oxygen there, though.
Would you like lose a hydrogen or something that has electrons on it?
Maybe. So hang on to that thought. So now we got to go all the way back to Gen Chem. I don't think you guys remember Gen Chem class, right? That's why you don't remember. You didn't have me. I knew it all along, right? So do you guys remember oxidation states, oxidation numbers? You guys remember talking about that stuff? Could you guys calculate one real quick if I asked you? See, now I asked you guys already live, and so now you guys are like, yeah, he's cool with it. Yeah, doctors, I got that. What's next? Right? But remember, to talk about what gets reduced or what gets oxidized, you have to take a look at the oxidation states. Right? So what you would do is you'd go through and look at the oxidation states for the individual atoms on here. Right? And then you could come back and say, well, the oxidation state became more positive, therefore it lost electrons, and so this is the thing that got oxidized, that kind of thing. Right? So remember, there's a tool that we have to have here to kind of assess what gains or loses electrons, and the oxidation states is what we use, that tool that we use to do that with. Right? Now the fortunate news is we don't really have to do that in organic chemistry. Okay? Organic chemistry, the definition of an oxidation is a little bit more simple, I guess. But remember, every time we simplify something, we lose the details behind the scenes, right? And so we do lose a certain, what's the word I'm thinking about here? We lose a certain level of knowledge, right? If we take shortcuts, you miss the scenery type thing, right? So that's kind of what it is. So how do we define an oxidation for us then? Well, what we would say in oxidation state is whenever we add bonds to an oxygen, right? Whenever we add bonds to an oxygen for a specific atom, okay? So we're taking a look at the carbon here. We'll mark that one in red, right? So whenever we add bonds to that red carbon, that would be considered an oxidation. Add bonds to an oxygen to that red carbon. Make sense? Did we add a bond to it? Yeah, right? We got a double bond, right? So we started out with one bond to an oxygen, now we ended up with two. Did we add a bond? Yes. Is that an oxidation? Yes. Okay. Can we add another bond to an oxygen? Could we add another bond to an oxygen to that red carbon?
No.
No, why not? What if I told you you could? You guys might consider me liars now, would you? So I'm telling you can add another bond to oxygen there. And as soon as I show you where it is, you guys are going, oh, all right, okay, right? You want to do that now? See, here's what I'm saying. I didn't say add another bond to that same oxygen, did I? I said, can I just add another bond to an oxygen, right? How many bonds to an oxygen does that red carbon have now? 3, right? Is that a valid functional group? Sure, it's a carboxylic acid, right? Could I add another bond to that? Whoops, I forgot to put the red dot there. Could I add another bond to that red carbon? To an oxygen? Yes, I can, right? Because how many bonds does carbon have? 4. So how many bonds in theory could I add to oxygen? 4. You guys got that, right? But what do we lose each time? What do I lose each time as I go from the left to the right there? I add a bond to an oxygen. Yeah, right? I have to lose a hydrogen on that carbon, right? You guys with me on this? Right, so if I go back and, right, remember, just because I didn't draw them in there to begin with, we never understood hydrogen stuff, correct? In fact, what do we have to lose each time? For the first one there, we have to lose what? 2 hydrogens, right? The green hydrogen on the oxygen, and one of the blue hydrogens, right? And then to turn the aldehyde into the carboxylic acid, we have to get rid of that hydrogen and add the OH to it. Now you guys told me that I can add 4 bonds to oxygen, so what would be the last oxidation I could do? What would that be? Yep.
Would you just have all OHs connected to?
What if you do like two oxygens but with two double bonds?
Oh, what would we call that? Carbon with two oxygens. Carbon something. What do we call it? Everyone take a deep breath. Good old carbon dioxide, right? CO2 is the most oxidized form of carbon that you can make, right? But you guys already knew that. What's one of the products of a combustion reaction? Carbon dioxide, right? Where does the oxygen come from? Well, the oxygen comes from the fuel source that you need to burn, right? Remember, to make a fire, right? Here's all your useful information, right? You have a fuel source, you need air, right? And you need heat, right? So carbon dioxide is the most oxidized form of carbon that you can make, right? That's why it tends to be a common product for a lot of these oxidation type reactions. We bubble off CO2 or you burn something and you make CO2, right? Now, practically speaking, right, we would probably not really want to turn this all the way into CO2, right? Although there is a reaction which we might learn later about, in fact, not might, we probably will learn about why it might be useful to make CO2. Right? But that's the most oxidized form of carbon you can make. Right? Now, what do we know about carbon and oxygen together?
They form a strong bond.
Yeah, they form extremely strong bonds. Right? Carbon-oxygen bonds are particularly strong bonds. Carbon-oxygen double bonds are very, 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 what's the word, I guess, favored, right? We want to make carbon-oxygen double bonds. Cool. So here's our task. Our task is now to oxidize things. If I have an alcohol, I can oxidize it up to 3 times, right? I can take an alcohol into a carbonyl, like aldehyde, right? I can take my aldehyde into a carboxylic acid, and if I keep pushing it in the right conditions, I can take it all the way to carbon dioxide, okay? And you're like, okay, that's fine, sounds great, how do we do it? So that's where we have the problem, okay? The problem isn't, can we oxidize an alcohol? It's, can we control the oxidation? Okay? Remember what we just said. We said that carbon and oxygen are bestest buds. They like to make bonds. And so if you aren't careful of the conditions of your reaction, you're going to push an alcohol all the way into a carboxylic acid or even all the way into CO2. It's hard to stop an oxidation at the aldehyde there. Okay? Because it wants to continue on and add bonds to oxygen, all these kind of things. So we have to be careful of the conditions. Make sense? Okay, let me ask a question then. If I oxidize this, what does it turn into? Like oxidize that alcohol, what would it turn into? Right? So take a look, right? Remember there's a hydrogen there. So you guys told me that when I do an oxidation, I have to remove a hydrogen from that carbon and make a bond to that oxygen. Got it? Good? Makes sense? Can I oxidize this? The answer is not really. What's different here? What's different between this particular set, right, and what I showed you guys up there? Okay? The difference is what? That hydrogen. Okay? Remember, to do an oxidation, you have to have a hydrogen around. You're like, hey, wait, Dr. H, you said the CO2. Remember what I said about the CO2 stuff? I said what? Under specific conditions, we can push it all the way there, right? It's got to be somewhat harsh, okay? Yes, we could take a carbonyl, a ketone all the way to CO2, okay? But it takes those same kind of harsh conditions. So the question, what kind of alcohol did we start out with here?
Secondary.
Oh, my efforts.
I can't with the other one.
Oh, yeah, oh. What kind of alcohol did we start out with here? What alcohol is this? Go ahead now. You got it. That's the second. Okay, you got it, right? Right, so here we got a secondary alcohol. On the other one, what did we start out with? Yeah, this is our primary one. Got it? So a primary, we can take into an aldehyde and take into a carboxylic acid. Okay? So a primary alcohol we can take into an aldehyde and into a carboxylic acid. A secondary, we can really only take that into a ketone. We can't oxidize that any further. Okay? You guys want to guess what my next question is going to be? There you go, you got it, right? So, what does this turn into when I oxidize it? Just add a bond between the carbon and the oxygen, right? Yeah, let's do that then, right? That seems easy. Dr. H. Clearly it turns into this, right? Jeez, I forgot all my chemistry, I was great. Right? What's wrong with this, of course? Yeah, violation of the octet rule, right? So will that happen? No. So a tertiary alcohol you can't oxidize. Why? What did we have in a primary and a secondary that a tertiary doesn't have? A hydrogen. So that's what you have to start to pay attention to. Okay? If you don't have a hydrogen on your carbon attached to your alcohol, you're not going to be able to oxidize it. So what does that mean? That means when we go through and we do oxidations, okay, a tertiary is not going to get affected by this. So we could say there's a certain selectivity that's available for oxidation of alcohols. Tertiaries aren't really going to react. So we don't have to worry about protecting them from oxidation and this kind of stuff. Okay? They kind of protect themselves, so to speak. Right? But primary and secondaries, we have to go through and be careful about how we can react those. Now a secondary, we can only take into a ketone, which is great. Right? But the primary alcohols where we really have to pay attention. Because there we have different conditions that will lead to different products. Okay? Whether we stop at the aldehyde or whether we go all the way through to the carboxylic acid. All right? So, let's talk about that real quick then. So, if I got my primary alcohol, and I take this and I put it in with some, let's do that. Okay, that's what we use. Sounds good. Okay. Taylor, can you see that? I can't answer. You can like comment on this. You're a Dr. H, it's fine. Right? So there we go. So condition number one. We've got an alcohol, we've got some sodium dichromate, right? Sodium dichromate, Na2Cr2O7. One of our polyatomic ions, right? Dichromate. But you guys already remember that, right? You guys are lying. Right? There it is. At the bottom, we got our good old buddy sulfuric acid. And we got some water. Right? So, what do we see about this? Well, we've got a chromium there, right? That's one of our transition metals. Okay, that chromium has a lot of oxygens around it. Okay. We've got some sulfuric acid, we've got some water. So, when you tend to see a transition metal with a lot of oxygens around it, it tends to be an oxidizing agent, okay? Things that cause an oxidation to happen, right? That's what an oxidizing agent is, right? It's an agent of oxidation. It causes something to happen. Which you guys already knew this too, right? Right? Yeah. I'll prove it to you guys that you already knew this. Well, maybe I'll prove it to you. Let me ask you a question. You guys remember how to do that? One of those weirdo reactions that came out of OChem 1. I think we learned about it after that. It was towards the end of the semester, I think. Yeah, correct. Yeah, this was kind of a weird reaction. There was only one special reagent that did this.
Is it the sindihydroxylation?
So that's so you could say that, right? That's it. So how do we do a syn dihydroxylation? What did you guys have? Huh? OSO4, right? And then we had what, like some DMS in there or something like that too, right? Oh, right, yes, right, that was one. Sulfite. Whatever, who cares, right? I don't need to know this crap, I'm a professor. I make the exams, damn it, right? It's something else in there, some kind of agent, or I think it's sodium sulfite. It regenerates the osmium tetroxide is what it is, right? So OSO4, what is OS? OS is osmium, right? Where's osmium? That's a transition metal, right? Does that osmium have a lot of oxygens around it? Yeah. Is this doing an oxidation? Are we adding bonds to an oxygen to a carbon? Yeah, so this is an oxidation reaction, right? It just happens to add two of the alcohols next door to each other. What was that other one you found there?
It was the KMNO4.
And what do we have? Water, right?
Water.
Hydroxide, and we kept it cold, right?
Yeah.
Okay.
So.
And that did something very similar, right? So we had two of these. What do you guys notice about the second reaction there? What do we have? A transition metal with a lot of oxygens around it, right? And then some of the other blah, 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 blah in there, right? And what does it do? Well, it does an oxidation. You guys with me? In fact, that permanganate oxidation there, the one at the bottom, the KMNO4, right? That's permanganate. We'll see that again in just a second. Okay? Cool. So whenever you're on your MCATs, and you're doing the organic section, and you're done crying, and you see a transition metal with a lot of oxygens on it, right? It's usually indicating that you're going to do some kind of oxidation. Okay, that's usually like one of these things to pay attention to. Okay, we have a couple different transition metals under different conditions, but they all tend to do some kind of oxidation. And so for here, it's not going to be any different. Now, here's what the product's going to be. It's going to take this all the way to a carboxylic acid. Sequentially, though. The first oxidation happens and it turns it into an aldehyde. But instantly, that aldehyde gets transformed into a carboxylic acid. we can't stop this reaction from happening. Okay? So, we're not going to know the mechanism for this. That's a little bit outside of the scope of what we need. But as this is going on, it makes the aldehyde, and then it continues all the way to the carboxylic acid. Okay? Do you guys get why I'm telling you that, though?
Because
It's not selective in a couple of ways. It's not selective in the means that it stops at the aldehyde. This dichromate will react with aldehydes and oxidize them to carboxylic acids also. Do you guys get what I mean by that? So if we have an aldehyde and an alcohol present in our molecule, it's going to oxidize both of those. Got it? Now sometimes you'll see this written as H2CrO4, chromic acid. So when you dissolve sodium chromate into sulfuric acid and water, you generate chromic acid in situ is what it is, right? In the mixture. Chromic acid is somewhat unstable, so you just make it while you need it is the kind of thing there, okay? So a good, cheap oxidation method. Sodium dichromate is dirt cheap, right? Sulfuric acid is cheap. Water is cheap. So I think you guys can guess what's going to happen here, right? So if we take a secondary alcohol under the exact same conditions, right, what's going to happen to it? Now, these transition metals tend not to be very selective. Right? So if it reacts with the primary, is it going to react with the tertiary? You bet. Okay? What's it going to turn a secondary into? Now remember, there's only one product we can make from a secondary, and that's what? A ketone. You guys got it? So, not selective at all. It'll react with it'll react with aldehydes, it'll react with primary, it'll react with secondary alcohols. In fact, it'll even react with more than that. If I find this stuff, I'll show you guys tomorrow. It's an impressive reaction. Just everywhere, right? So, very, very fast oxidation. But it's actually kind of useful. It has its certain uses for it, right? So, I don't want to be dismissive of it. All right, let me zoom out here because that looks a little bit bad. All right, so we're going on here. We're going to really change things up. Whoa, okay? We're going to do the exact same thing and we're going to heat it up. Wow. So, what do you guys think is going to happen? Aha! You think an oxidation is going to happen, okay? So now we've got a transition metal with a lot of oxygen. Different conditions though, right? You guys see that? The first one's under acidic conditions, right? This one's under basic conditions. That could be a useful distinction, right? But now we have to warm this up. Okay, what does it mean to warm something up? 40 degrees Celsius? Sure. What does it mean to keep something cold? 10 degrees Celsius? Right? You guys get the point? What does it mean when something's hot or cold? It's a bit arbitrary, right? So the point being this, right? If we heat this up, it'll do a certain reaction, okay? If we cool it down, we just slow that reaction down. It doesn't stop it. Right? You guys remember the light and the hot versus the dark and the cold for your halogenations there, right? Why did we have to keep things cold and dark? Well, that prevented the one that happened at the hot from happening. Right? So it's kind of the same idea here. Remember, whenever you heat something up, every reaction goes faster. Okay, when you cool it down, you just slow down certain reactions. Okay? So here, it's going to take this all the way into a carboxylic acid, right? With a slight, well, let me be technical about it, sorry. It's going to take it into a carboxylate, or carboxylate. I don't want to make a mistake, I'm recording. Can't deny it. What are you talking about? Why would this make it to a carboxylate and not a carboxylic acid?
Because
It's under basic conditions, right? You generate a carboxylic acid, but are carboxylic acids acids? Yes, doctor. Okay, right? So how do acids react? Like acids, and if you're under basic conditions, what's going to happen very, very fast? That acid-base reaction. You guys got it? Right? So it's going to oxidize it to a carboxylate, and then through the workup, you guys would do an acid workup to regenerate the carboxylic acid from it. So you'd add like HCl to it or something like that, right? And then you guys could extract out your carboxylic acid. Got it? Cool. Okay. So how does this work? Well, pretty much in the exact same way, right? It goes through the aldehyde and then oxidizes itself to the carboxylate, right? So what does this mean to you guys? How different is chromic acid versus a permanganate oxidation? The answer is, really isn't, right? I don't know, yeah, OChem 2 is easier. Like all these reactions do the same thing. So what's in common between these two reactions? What are some of the common traits of these two reactions?
internal functional groups.
Yeah. In terms of the reaction conditions, though, what do they share in common? So we talked about the transition metals, right? What else?
They have a group 1 metal.
Ah, interesting. So a group, we would say group 3, right? Yeah, but you're absolutely correct. Yeah, they're first row transition metals there, right? Chromium and manganese are both in the 3D metal line. Yes. Good observation. Very good. What else?
Water.
Ah, water. That's going to be your other key thing to pay attention to. Okay? Any reaction conditions, any oxidation conditions that have water as part of it, pretty much means you're pushing it all the way to the carboxylic acid. Okay? I'll show you guys what I mean with that in just a second. But if we remove the water, then we can control the oxidation and usually stop this at the aldehyde. Got it? So take a look for the water. That's kind of the clue for this. Okay. So let's take a look at one of these controlled reactions then. It's not going to look all that different at the beginning. But this is going to be one of your guys' favorite reactions, and I'll tell you why in just a second. Okay. There it is. Nice, right? So what in the world is this? So PCC is something called pyridinium chlorochromate is what it is. Pyridinium chlorochromate. So let's break that down for just a second. Here's a pyridinium. It's a protonated chlorochromate. Okay? If I remember correctly, that's how it looks. Do you guys know any better? That's what I thought. You guys gotta get, I'm just teaching you guys complete BS, right? They're like, oh yeah, piece. No, just kidding. No, that's what it is, right? Pyridinium chlorochromate here, right? Cool. Okay, tell me what you guys think about this. Okay, it's ionic. But the other one was ionic too, right? Because instead of a pyridinium, we had a what? The sodiums, right? Or the potassiums are the other ones, right? Remember, sodium and potassium are just counter ions. Okay, so to balance the charge, what's the pyridinium doing in this case? Balancing the charge, right? What else though?
There's a chlorine there.
There's a chlorine there. That's going to probably end up doing something along the way. Probably a good leading group and stuff like that, right? Chromium is a transition metal. What do we notice about that chromium? It's got a lot of oxygens around it. So how is this really different than the other reaction? Right now you'd say what? It isn't, right? This is a heavily oxidized transition metal. Why is this different? What is not part of my reaction? Water, okay? So here's the difference. The difference is when I run something like PCC or its brother PDC, which is pyridinium dichromate, okay? So pyridinium dichromate, not that it really matters. We run this in CH2Cl2, which is our good solvent, DCM. All right, here's your word salad for the day, right? PCC, DCM, PDC, right? I'll show you DMP in just a second. Like, I'm good, thank you. Right? So what is all this stuff? Okay, so PCC just stands for the pyridinium chlorochromate, right? DCM is dichloromethane, DCM, CH2Cl2. Okay? Have you guys seen dichloromethane before? Yeah, you guys have used it in the lab quite a bit, right? In fact, you guys used it when you were doing extractions with a SEP file, right? Now, DCM is not miscible with water. It's a very dry solvent, right? Water doesn't stick very well into dichloromethane, into DCM. Okay? So guess what's not part of this reaction? Water. If you had water in here, guess what it would do? Take it all the way to its complete oxidation, right? You guys with me on this? So we change a solvent to exclude water. Now your immediate question should be what? Well, why don't I just change solvents and take water out of the other reaction conditions, right? Wouldn't that make sense? Well, the problem is your KMNO4 and your sodium dichromate aren't soluble in DCM. That's the difference. That pyridinium there makes these soluble in organic solvents. Okay? So then we can put them into a water-free condition and then do the reaction. Okay? So why are these useful? So PCC and DCM or CH2Cl2 will oxidize to an aldehyde and stop. Okay? PDC will do the same thing. Why would you use one over the other? I don't know. Just whatever day it is, I suppose. Oops, I'm a little bit ahead of myself. These also work with secondary alcohols. Not that we have to worry about them stopping necessarily in this case, right? Good. Nice selective oxidation. Sort of selective though, right? It still oxidizes both primary and secondary, but it stops it at the aldehyde. So now you guys have a way of directly turning an an alcohol into an aldehyde, without having to go through that whole spiel of making an alkyne and kind of going that backwards right there. Make sense? I'm sorry, I have to look this up. I forgot what the structure is before I show you this next one. So, talk amongst yourselves. Oh, there it is. I almost had it correct. Okay. So there's another one to kind of lump. Before I add that one there. So there's another reaction that works with these kind of, I don't know, what do you guys want to call these? The 3-letter oxidations, right? There's another set of reactions that go with these 3-letter oxidations. But it works the exact same way, right? You have an OH, you put in something called DMP, right? And it works with primary and secondary also. What solvent does the book use for this? Oh, it uses DCM also. Okay, of course it does. There you go. That's a good way for you guys to remember it then, right? There's something called DMP, which stands for Martin, for the name of the scientist who discovered this. Iodine. So of course it does. So here's how DMP looks. This looks done. What's it? Okay. Now, do I expect you guys to write this in your notes? Nope. Do I expect you guys to know this? Nope. Making a point with it. Okay. I mean, put it in there to impress your parents. Like, look what I learned. That's nice. Go back to your room, right? Right? What do you guys see in this compound, though? See an iodine. And what does that iodine have around it? A lot of oxygen. Do you guys get kind of the pattern here? Right? You see one of these atoms that has a lot of oxygen around it, which is probably going to do some kind of oxidation. In fact, there's a whole class of compounds called hypervalent iodines, right, that deals with, remember iodine I should say, is this massive atom, right? We can do a lot of weird chemistry with iodine, right? So it's not unusual at all to see these kind of odd oxidation states and odd valencies with iodine, right? And so there's a whole class that kind of deals with using the hypervalent iodine to do chemistry with. Okay. So you don't need to know the structure, but there it is, right? You see an atom with a lot of oxygen. It's kind of one of these clues. Okay, I'm probably going to be doing an oxidation. Okay. So again, the trick here is we remove the water as part of the solvent. Okay, that's the key to this. Got it? But these all kind of share a problem, and the problem is kind of something that's behind the scenes. The older I get, the less relevant the reference is. Oh, crap, now I'm forgetting the name. What's the name of that movie with the female lawyer with like the water and the, oh my gosh, what is this? Yeah, that's it. Yeah. Oh my gosh, no, it was like a movie in the '90s that like everyone kind of made everyone. I'll look it up here. Geez, talk about a flopped reference. But the point is, there was this company who was basically dumping waste into a river, and it was poisoning. It's based on a true story, right? That was kind of the catch with it. And they were basically dumping chromium waste into a river, and chromium is highly toxic, right? Highly toxic. Hexavalent chromium. And, all right, I gotta look this up. All right, this will be easy. Don't worry. Go ahead and talk amongst yourselves. Right? Aaron Brockovich, that's who it was, yeah. You guys don't remember that reference? It's close to legally blind. No, but it was a movie based off of this and everything. So anyway, but the point is, any of these chromium compounds are very toxic. And so when you use them in the lab, you have to be careful, right? You have to separate the waste out, and it goes into a separate waste stream. And then when you inform the company to come pick up the waste, and say, hey, there's chromium, and they're like, okay, give us an extra $1,000 to dispose of it. So it causes these other problems down, down the way. So if we can get away from any of these transition metals, then it makes our life a little bit easier. Okay? And so there is a common set of reagents that we can use to actually do an oxidation without any of these transition metals in it. And it's actually the preferred way of doing it. So we have what's called a Swern oxidation, is what it is. So again, these names are just coming after the people who discovered these, right? So, what's a Swern oxidation? We got a little bit of a word salad here too that'll start to break down for you guys. So it's a two-part reaction. We have Dmso and COCl2. And then the second part is triethyl NET3, okay? Oops, well, I didn't mean to put that in a circle. Not that it really makes a difference, but yes, there's a technical distinction. Numbers in a circle indicate a charge. Right? After parentheses, just means a different step. All right. See, more letters. Yeah, what's up?
What's the bottom one?
NET3. I'll break it down for you guys here in just a second. Okay? So, what this will do, again, you'll notice there's no water in here, right? So this will be another controlled oxidation. So we'll take a primary alcohol into an aldehyde, is what it is. Okay? And we'll take a secondary into a ketone. So we'll stop at the single oxidation in both of these cases. Now some of this stuff you guys might already recognize. Now Dmso, we've seen come up as a solvent before, right? So this is dimethyl sulfoxide. Right? So it's just a very common solvent. It's a polar aprotic solvent. It's got a high boiling point. It tends to be used quite a bit in biology and biochemistry labs. And so it's a common solvent that you pretty much find in any organic chemistry lab. Dmso is always around. Okay? COCl2 is oxalyl chloride, which looks like this. Kind of a weird looking structure there. But it is a derivative of oxalic acid. We'll talk about how to, that's a new functional group I don't think we've talked about. Those are called acyl halides. We'll talk quite a lot about them later on in the semester. But you see there are a carbonyl group, right? We see that C double bond O, and then we've got a halogen coming off of one side of it. You guys want to take a stab at what that halogen is there for? Probably as a leaving group, right? That's all they do in life, is act as leaving groups, right? So the same thing here. These are very reactive carbonyl groups, okay? But it's a cheap material, oxalyl chloride. Oxalic acid is found everywhere in nature, or not everywhere, but in a lot of places in nature, right? And so making oxalyl chloride is pretty darn cheap and easy to make. There's a reason why I'm pointing all this out. NET3. This is triethylamine. So we have this, right? And thankfully it stops at only 3. Otherwise we have different explanations to make. Yeah, all right, thank you. All right, so it's got 3 ethyl groups coming off of a central nitrogen. Okay, so your amines are organic bases. So whenever you tend to see an amine, like remember we had pyridine last semester when we were doing that, when we were making tosylate, right? They were acting as a base. Amines are very basic. Okay. And so the triethylamine is an organic base that is soluble in organic solvents. Okay? In theory, you could use something like sodium hydroxide, but it's not soluble in these solvents that you need it to be in, right? So you use triethylamine. Now, triethylamine is known for two things. One, it's in every single organic chemistry lab ever. It's just one of these very common bases that's used in a billion different reactions. The second thing is it stinks like dead fish, okay? Like all these amines have a very unique smell to it, right? So it's very noticeable and just, I don't know, right? I've got a big nose, so I remember these things. Right? So anyway, so what's the point that I said with all these things? These are found in every lab, okay? So you're working in the lab when you guys all become, go to graduate school for chemistry, right? Well, nobody disagrees, all right, good, right? You guys are like, yeah, that sounds good. I do hate myself. I'm joking. Grad school is fantastic. I liked it. Right? No, it was awesome. Right? You get paid to go to school, right? You get paid to go learn and get a PhD. A lot of your core sciences, they pay you to go get your PhD, right? So you don't have any student debt walking out with a PhD. It's pretty nice, to be honest, right? So, in fact, they pay you to go do it. Now, the difference is you have to go teach undergraduates, and that's miserable. It's absolutely miserable. I mean, no, I'm joking. No, but that's the trade-off, right? You're actually hired by the university to go be a teaching assistant, is what it is, right? But you get paid to go to school and you get a PhD walking out, right? It's nice. But anyway, the point being, if you're working on your PhD and you're in the lab and you have to do an oxidation, you will find all of these things on the shelf. You don't have to order it, you don't have to worry about chromium and acids, right? This stuff is just sitting on the shelf. You put it together, you mix it in there, it does the oxidation. It's a very, very, very nice, simple reaction, right? It's very selective, it's mild conditions, right? So that's something you start to read in the book, and then I'll probably start to mention along the way, right? These are mild oxidative conditions, okay? There's no sulfuric acid in here, right? There's no sodium hydroxide, right? That's what I mean with that. Like these harsh conditions where you have unselective reagents, okay? So a swirl oxidation is the preferred way of doing the oxidation, is usually what it is, okay? We avoid the metals and we avoid all that other shenanigans, okay? Cool. So what else do they kind of talk? I think that's kind of all they have mentioned about those, yeah? So that's good. So there are your oxidations, right? So we have, kind of just to zoom out here, way too much. Perfect, right? That's really helpful. All right. So just real quick summary then, right? If we have the transition metals with the oxygens around it. These are unselective, they have water in them, right? They're going to oxidize completely to the carboxylic acids, okay? You have your three-letter word salad reactions here, like you have your PCC, your PVC, your DMP. Any of those are pretty much fungible for us, right? We can swap one for the other one. It's not going to make a difference, okay? They're running the same solvents, and the solvents tend to exclude water, which is what makes them appealing, right? And then we kind of have the preferred method, right, of the Swerin oxidation there, and that's just preferred. Remember, we're doing chemistry on paper, so who cares about chromium, right? But if you're in the lab and they're doing it, then it does make a difference there, right? That's the point with this, okay? So there we go. Now we've taken care of half of these reactions, right? You guys catch what I mean with this? All these reactions do what? Oxidize, right? So guess what we have to do then? We got to do some reductions, okay? So we got to go in the opposite direction then. Now the reductions are a little bit more straightforward-ish. So we'll start with kind of the nuclear bomb of reduction, right? So just like we started the oxidations with these kind of, let's say, unselective conditions, right? The things that oxidized everything without discrimination, right? There's a reagent that does that with reductions, that you see it in reductions over and over and over and over and over again. And we'll see it in this semester over and over and over and over and over again. And it's another word, another alphabet soup here. It's LAH, okay? Now, LAH is lithium aluminum hydride, right? Lithium aluminum. Okay, so let's break that down. What's lithium? Well, lithium is Li, right? We know it's a group 1A metal, so it's usually going to be there in a positive charge, right? Got our buddy aluminum. Okay. And now, what in the world is a hydride? Hmm?
H
Mm-hmm. H with a lone pair and a negative charge, okay? So if we put all this together, we have to remember that aluminum is always going to be a 3+ charge. Okay, so if you put this all together to make LAH, we have LiAlH4, okay? So that's what LAH is, lithium aluminum hydride. And that's important to recognize. And it's going to help explain why, to a degree, LAH reduces everything. Okay? How many hydrides are there per equivalent or per mole of LAH? 4 of them. Got it? If one of those hydrides is going to react, all of them are going to react. Okay? We can't stop those hydrides from reacting. And boy, do they want to react. Okay? LAH is one of those things where using it in Florida is always interesting, because Florida tends to be humid, as you guys might be aware. And LAH is super reactive, to the point where on humid days, if you take LAH out, it might catch fire, right? So it's like, not like kaboom, right, but it'll kind of fizzle and spark, right? Because it's reacting with the moisture in the air. Like super duper reactive stuff, okay? Which is good in some cases, right? Because it tends to be that the more reactive something is, the faster the reaction goes, right? Something can be a nice reagent, but if it takes 2 weeks for your reaction to finish, guess what? You're not going to use it, right? You don't have 2 weeks to waste on this stuff, okay? So LAH tends to be a very reactive reducing agent. That is its purpose in life. In fact, whenever you see hydrides, they tend to do, well, they're useful for 2 things. They're really powerful bases, and they are good reducing agents. That tends to be their utility in life, okay? But you guys already knew that, right? Yeah. What's an oxidation? In our definition in organic chemistry, what's an oxidation? Adding bonds to oxygen, right? Okay, so what would a reduction be then? Removing bonds to oxygen, right, but adding bonds to what? Hydrogens might be a good definition, okay? Hydrogens will be one of the things that we typically add bonds to. We'll see another example for reductions also, okay? So adding or removing bonds to oxygen is good. Adding a bond to a hydrogen is a reduction too, though, okay? Cool. You guys ready? I've talked too much. Okay. See what you guys come up with. See if you guys can get a very complex 2 arrows to show me that mechanism. Yay, technology. Sometimes. here to here.
Oh.
Nothing else in between. Be careful, show me the hypervalent exclusively. I'll show you this, you got the right idea, but show the individual part that's working there. What's the LAH look like, right? That's the question. Do we care about the lithium? Sort of. Lithium's got some interesting properties, which will. Right, there's our buddy ALH4, right? So how's this going to look? We attack the carbonyl carbon and we kick up that bond, right? So we make a bond here to that blue hydride to begin with. Got it? You guys with me on this? Now we know that oxygen's not just hanging out there with a negative by itself. There's a couple things going on. Aluminum loves oxygen. Loves it. Loves it. But you guys already knew that too.
Is there supposed to be negative charge in the aluminum?
Oh, well, yeah, the whole thing. Yeah, you can roll it on there, that's fine. Sorry, I thought you were talking about the individual atom. Yeah, that's fine, you can put that there. Oxygen loves aluminum, okay? So whenever you see an O minus and you see some aluminum around, those things are going to be making bonds, okay? The lithium's kind of hanging out, just balancing things, but lithium actually really loves oxygen also. But you guys already knew that too, right? Because ever seen those lithium fires that happen when like batteries get ruptured and all this kind of stuff? Yeah, lithium's an interesting beast. Okay. What's the problem with what we have though? Got an O with a minus charge. Is that what we want? No, what do we want? An alcohol, right? An OH. So how can we turn an O minus into an OH?
Give it a positive proton.
A positive proton. Is there any kind of compounds that can do that?
Acid?
Oh, an acid. Okay. So here's a common thing that we'll start to see happen in the second semester. We'll have to start adding in acid workups. Okay. So aqueous acid workups, the book talks about that kind of stuff. Okay. But we'll have to start adding in acid workups. Typically, you'll just see it as H3O plus, something like that, right? You might see it as just H plus. It kind of all means the same thing, right? And then we take our O to an OH, okay? Aha, Dr. H. I figured out a way to increase my efficiency. I'm going to just add H3O plus over here, right? I'm just going to put LAH with H3O plus together and make life easier. Why can you not do that? What is LAH, first and foremost? A hydride, right? Are hydrides powerful bases? You bet. What do we know about H3O plus? They are really strong. What happens when you put powerful bases and strong acids together? Violent exothermic reactions. What's the byproduct of this violent exothermic reaction? H2, hydrogen gas. Now what do we know about hydrogen gas? And an ignition source, right? If you mix H3O plus with LAH together, boom, right? You're instantly going to generate H2, and if it's in a large enough quantity, you generate a lot of heat, and then what do you have? A big problem, okay? So you cannot mix those two together, right?
Somebody's not on purpose though, because the one is like a bomb or something.
That's a stupid bomb, because as soon as they mix it, it'll just right under themselves, right? Like, oh, knock yourself out, keep trying, buddy, right? So often what you'll see is you'll see this kind of separated out as separate steps there, right? So when you guys see the step 1 and step 2, that means step 1, you're doing the reduction, step 2, you're doing the acid workup, okay? You have to be deliberate about this because it's going to behave completely differently if you mix the two together at the same time. In fact, it's not going to do anything, okay? You guys with me on that one? Cool. All right, I think that's a good place to stop. We'll pick up the, so lab tomorrow, right? You guys done your pre-labs? Pre-labs that are for every lab, you guys already know this, yes? Okay, remember there's these pre-lab forms outside my office that are printed out for you guys to grab if you need. Okay? So don't forget to bring those, and I'll see you guys tomorrow. We'll do the safety stuff, and we'll go through the soap making lab, right? Cool. All right.